Just go in presentation. Yeah, perfect.
There we go. Perfect. Thanks for the introduction, and thanks to all attendees for joining this, I would say, somewhat exotic session this morning, at least exotic in the context of this conference. But I hope myself and Caro Löscher after me can convince you that the ocean can be a very powerful ally in our efforts to reach the goals of the Paris Climate Agreement. Let me set the stage by reminding us of the emission pathway that we need to take to stay below 2 degrees warming. And this is kind of a rather simplistic, but I think rather illustrative graph of what it takes to stay below 2 degrees warming. You can see here presently we're hopefully at the peak of greenhouse gas emissions. And if from now on we take a very aggressive approach of reducing CO2 emissions, the green area here shows you what we are likely to achieve using all the options that we have in terms of conventional abatement technologies. You also see that there still remains some CO2 emissions, even if we are on this rather optimistic pathway. There still remains some greenhouse gas emissions, partly from CO2 emissions directly, but to a larger extent, and that's kind of the intermediate bar here, from other greenhouse gases like methane, nitrous oxides, and others, which are likely to still remain even if we go the most aggressive way in reducing CO2 emissions. Because we will unlikely stop planting rice and consuming milk products or eating meat. So those emissions are likely to continue. To actually reach the goal of staying below 2 degrees warming, you also see here at the bottom of this graph, the blue panel, that we will need to phase in as early as 2030, so just about 10 years from now, some what's called negative greenhouse gas emissions. So we actually need to take out CO2 and other greenhouse gases from the atmosphere actively to even be able to reach net zero emissions in the course of the century. So that is consensus, I think, in the scientific community at the moment. We will not be able to achieve the goals of the Paris Agreement without those negative emission technologies. And let's have a look what the options are in terms of doing that. At the moment, research on CO2 removal technologies is entirely focused on land-based approaches. And most of you have heard the options of afforestation and how much this could potentially contribute. Many people have heard, and the IPCC report strongly focuses on BECCS as an option, bioenergy with carbon capture and storage. Surprisingly, I would say. There's other options like air filters combined with carbon capture and storage, very expensive, energy expensive. So not sure whether this is our best approach. It may change with time. And there's biochar and many other options. That's where the focus sits at the moment. But we also know that the biggest buffer in the climate system in terms of mitigating human impact is the ocean. The ocean presently takes up 90% of the excess heat that we produce through greenhouse gas warming, and it takes up 1/4 of the CO2 emissions that we emit every year. So it's already doing us a great service, which comes at a very high price for the ocean, because warming and acidification have strong impacts on biology and biogeochemistry in the ocean. But it's also clear that the ocean not only has a higher potential for carbon dioxide removal than land-based options, it probably also has less conflicts of interest. When you just think of space limitation on land, other interests like agriculture and urbanization on land, these conflicts of interests are less severe in the open ocean, at least if you exclude coastal areas where there's certainly also high interest. Still, despite these high potentials, the research on ocean-based CDR approaches are at the very start still, and in most cases haven't even started yet. Any approaches that we may take, be it on land or in the ocean, need to fulfill a number of criteria, and I thought I would have that here. Maybe it's the next one here. Yeah, let me start with this first. A list of criteria that need to be fulfilled in order to be considered as a useful CO2 removal approach. They need to be effective, whether on land or in the ocean. They need to be scalable, and scalable is usually considered any approach that doesn't at least sequester 1 gigaton of CO2 per year, is not anything that would help us out of the dilemma. The CO2 sequestration needs to be permanent, or at least should last for a long time, hundreds of years ideally. It needs to be economically feasible, meaning it shouldn't cost way more than well, certainly avoiding CO2 emissions is the least expensive, but it should be in that range. So these three criteria really fall under what I would call technological development. It needs technology to make progress on this side. It needs monitoring and governance to ensure that whatever approach is taken is verifiable, and it must be auditable and accountable. So also the governance is not really worked out at this point. And then any approach taken must be environmentally friendly, and the disbenefits of using it must clearly outweigh or the co-benefits must outweigh the disbenefits. So we should not harm the environment with taking any of those approaches to a large extent. Let's have a look at what the options are in the ocean. This is a kind of a nice summary of the various options we might consider taking in the ocean. There's a whole set of what we call blue carbon approaches, and most people would probably agree that this is a good way forward. These include kind of regrowing mangrove forests, expanding seagrass meadows, and making kelp forests grow more extensively. All good options, useful to consider, but as I will mention a bit later, the carbon dioxide removal potential of these is probably low. You can also use marine biomass for biochar production. Same constraints. If you can't really scale it up, why would you use it for biochar? Likewise, marine biomass for bioenergy and combined with carbon capture and storage. The limitation here most likely is the amount of biomass you can produce this way, and so probably low potential. A more chemical approach is extracting CO2 directly from seawater, which is beneficial to doing this in compared to the atmosphere because of the much higher concentrations of inorganic carbon, DIC, in the ocean. So it's less energy consuming, and then you have to combine it with some CO2 storage, for example, below seabed, as indicated here. And then there are the more open ocean-based approaches that you see here on the left side. Artificial upwelling or downwelling is one option, probably low capacity, terrestrial biomass dumping. Not sure that's ever going to be feasible. You need to first produce the biomass on land with lots of conflicts of interest on land. And then there are ocean alkalization, alkalizing the ocean with some minerals, and iron fertilization, adding iron into the ocean and making phytoplankton grow as a result of that. So those are the options that can be considered. And I would like to, if I can make this go forward, kind of walk you through these. Don't be scared by this huge table. I don't want you to look at all the different options. Just on the left side, again, you see the various options I've just mentioned here. And in the upper panel, you see the criteria under which they are considered for as carbon dioxide removal approaches. So there's the physical potential for carbon dioxide removal. There's the economic feasibility. What's the price per ton of CO2 sequester? Political and legal constraints, public acceptance, environmental impact, and social impact. And if you just take a kind of a quick look at the table, you see that there's a lot of unknowns and quite a few lows or unclears in this table. So this kind of shows you where we stand with this research on ocean-based negative emission technologies. If you look at the very left panel here, the physical CDR potential, and we walk through this quickly together, you see it starts with low. This is going faster than I wanted. It starts with low for artificial upwelling, unknown for downwelling, again, low for blue carbon sink enhancements, CO2 direct removal is unknown, potentially high. Biomass for biochar is likely low. For CCS, also likely low. Then you see a low to medium for iron fertilization. You see an unknown for terrestrial dumping, and you see a high for ocean alkalinity enhancement. So these two, the bottom two really stick out. And for the remainder of the talk, I'd like to walk you through these two options, iron fertilization and ocean alkalization. The first one, iron fertilization, because this is really the one that has been studied the most intensive so far. And the latter one, ocean alkalization, because that's the one that is given most attentions in the marine science community at the moment because of its high potential and possibly low impact. But the latter we don't really know yet. So let me start with iron fertilization. The basic concept, the basic idea of that is that large parts of the ocean lack this micronutrient iron. They are kind of rich in all other nutrients. And here on the right side, you see a map of the global ocean, and all areas shown in red and yellow here are areas which have all nutrients needed by phytoplankton in excess, except of iron. So they're just lacking this micronutrient iron. So in these areas, you could actually dump iron, release iron, and there's plentiful of iron from various industries as a waste product, iron sulfate, for example. You could inject these into the surface ocean. This would make the phytoplankton grow, take up the excess nutrients, and part of that phytoplankton that has now bound the CO2 that it needs in photosynthesis sinks out into the deeper ocean. The CO2 that was taken up in the surface will then be replenished by CO2 from the atmosphere, and the carbon that is drawn down with the sinking particles will be remineralized in the deep ocean. So the CO2 will be released in deeper waters. So it's what we call enhancing the biological carbon pump, pumping down CO2 through organic matter into the deep ocean. That CO2 remains in the deep ocean depending on where you do this for timescales of centuries to a couple of 100 years. So not permanent, but at least it would help us to get through this transition phase that will be the most critical for the next coming decades. And if you look at the CO2 removal potential of this option, I mentioned before, it's low to medium. In fact, the most recent estimates give this as maximum 4 gigatons of CO2 per year. That's when you really fertilize large parts of the Southern Ocean around Antarctica. If you compare this to present CO2 emissions of 36 gigatons of CO2 per year, it can make a contribution, but certainly not be a solution to the problem. And the cost is not really cheap. It's given between 50 and 200 euros per ton. Some estimates even go up to 500 euros per ton, in which case it would not be economically feasible at present CO2 prices. Okay. But as I said, this approach has been tested quite widely already. This is a map of the iron fertilization field trials that have been done until today. There are 13 in total scientific trials, purely scientific, not for the purpose of sequestering CO2, and 2 commercial trials that have actually tried to make money with it. They have altogether, at least the scientific trials, have shown that in principle, the approach works with adding iron in these areas that you see here with the red dots. You get increased algal growth. You get also a shift in the phytoplankton community towards diatoms. That was a very similar response seen in all iron fertilization experiments. You also see a drawdown in CO2 in the surface layer, and they all have shown enhanced sinking of organic matter to depth. But none of them, despite this massive international efforts, 13 field studies with each one, many scientists, up to 50 scientists involved in this, none of them have actually been able to show evidence for long-term CO2 removal. So we still don't know whether it works on longer timescales, whether it fulfills the requirement of long duration. Presently, there's kind of a moratorium on these kinds of experiments, so no further research is being done on iron fertilization anywhere in the world, as far as I know. Certainly not in Europe and North America. There are a number of risks associated with this approach, such as changes in the food web structure. That's kind of a given. If you shift the community to diatoms, that will automatically result in a change in the food web structure. That does not necessarily have to be a disbenefit. It also includes that you have more food for fish and whales, which could be seen as a good change. It's kind of a natural change because you also have in these low iron areas, you have natural occasions of CO2, of iron addition, for example, in the wake of islands. Then you also get this change in food web structure and increased trophic transfer to higher trophic levels. There is a risk of harmful algal blooms. None of those 13 field studies has actually shown this to happen, but potentially the risk still remains. There's certainly enhanced deep water acidification and deoxygenation if you follow this approach, because if you want to sequester CO2 in the deep ocean, it will consume oxygen and you will increase acidification in those waters. That's kind of a given. There was the fear of production of other climate relevant gases like nitrous oxide. That was not seen in any of the study, well, except one study showed a slight increase in N2O production, but that still needs to be verified in more detail, I think, to be sure that it doesn't happen. It also probably depends on where you actually apply the approach. And then long-term, there are likely to be downstream effects on nutrient availability. If you use the nutrients in the Southern Ocean over a long period of time, then the water that downwells in the Southern Ocean and will eventually upwell in lower latitudes, equatorial areas and upwelling areas, for example, will have less nutrients in it. So 50 to 100 years down the line, you will have these downstream effects. Which clearly should be considered a disbenefit for those areas. So those are the drawbacks of this approach, and you've seen the potential benefits in the slides before. At the moment, this approach is highly controversial. Most marine scientists will not support using this as an option for CO2 sequestration. And as I said, the research has basically stopped internationally on this approach. The opposite is true for ocean alkalinity enhancement, where the research is just picking up and is reaching quite a bit of momentum already. The approach can be applied pretty much anywhere, both in coastal waters, for example, on beaches, release some mineral along beaches, and this is being discussed, in fact, in the Netherlands, where they do a lot of moving of materials along their coastline. So you could easily include some minerals that do the job of alkalizing the ocean. It can be applied from certain factories, for example, connected to desalinization or cement industry. It could also be applied open ocean, where you just release this, for example, as part of the ballast water that all ships take in and let out again before they enter a harbor. So this would be an option where it could also be done with the existing technologies. It's in a way a low-tech approach. And it's certainly a process that nature does itself. So we would call it a nature-based approach. And what we call it in nature is weathering. So it's basically minerals, some rock, being weathered through consumption of CO2 and through water. So the two ingredients you need to weather rock are water. It has to be moist, and you need it's consuming CO2 according to the reaction that you see here. This is just one example of a rock. You can take any kind of basalt you like, or calcium carbonate based mineral. It consumes CO2 and water, and it releases a number of ions, which eventually will be via rivers, will be supported into the ocean and are actually taken up in the ocean by organisms that need these minerals for their calcification or silicification, which then closes the cycle once those biominerals are sinking to the deep ocean and then kind of get reworked into the terrestrial cycle. The natural weathering at the moment, so the amount of CO2 taken up by the natural process is about 1 gigaton of CO2 per year. And there's presently no indication that this number increases in significant amounts. It's a bit temperature dependent. So as it gets warmer, it will slightly increase, but still the amount of sequestration through natural processes is considered to be kind of in balance. So not helping us in balance with natural cycling. So not helping us to reduce the atmospheric CO2. The key question is, can we speed this process up? Can we enhance the weathering process to an extent where it actually takes up more CO2 and can take up a significant part of anthropogenic CO2? There's a number of minerals that can be utilized to do this, both man-made minerals like quicklime, which is an intermediate product of the cement industry, limestone, which we find naturally, like you see here on the right side, the White Cliff of Dover, or silicate-based minerals like magnesium olivine that you see here in the lower hand. They all have the potential to take up CO2. Quicklime can take up 2 CO2 per mole of quicklime. Here you have to keep in mind that to produce quicklime, you first need to burn calcium carbonate, and that releases 1 CO2. So the net sequestration is, as with limestone, only 1 CO2, except that you also need to invest a lot of energy in terms of burning the limestone to get quicklime. But quicklime easily dissolves in seawater, so it's one highly rated mineral that could be utilized for this purpose. Limestone, there's plenty of it on land, but also in the ocean, which naturally dissolves as the ocean acidifies. It sequesters 1 CO2 per mole of calcium carbonate. And for the silicate-based minerals, depending on which one you use, for every mole of olivine, for example, you can sequester 4 moles of CO2 and then release mostly bicarbonate. That's kind of the form that the CO2 then ends up in. And the bicarbonate, once flushed into the ocean, permanently stays there. It does not kind of go back into CO2. It does not release the CO2 back, but it carries that signal of bicarbonate as long as the alkalinity that you add with this process through the calcium magnesium stays dissolved in seawater. So it fulfills the criterion of long-lasting, if not permanent CO2 sequestration. The kind of effort that needs to go into doing this is massive. It's basically duplicating another industry like the cement industry or the changing of coal into electricity. It's on that scale. As you see here in those photographs depicted here. The potential for CO2 removal is huge if you are considering to do these massive mining efforts that's seen here. The biggest cost in terms of CO2 footprint or energetic cost is really the milling. Not so much the mining, not the distribution, but milling it down to particle sizes that easily dissolve, for example, in the ocean, or if you sequester it, or if you distribute it on agricultural fields, you need to grind it down to particle sizes smaller, 10 micrometer. And that's really the biggest CO2 footprint of this approach. The material you need per ton of CO2 is between 1 and 5 tons. So basically just duplicating the amount of fossil fuel we're kind of mining and transporting these days. You can see it's a huge industry that is needed to do this on land. The estimated costs are, depending on which approach you take, relatively low, between 5 and 100 euros per ton of CO2. What we don't know at the moment are what environmental risks are involved. We can imagine the environmental risks on land. I mean, it has a high burden, obviously, if you do the mining of this much of basalt or calcium carbonate. But what are the environmental risks in the ocean? And to address this, we are presently conducting a study on the Canary Islands, and that's where I'm sitting at the moment, with what we call mesocosms. In this case, our small mesocosms. We have offshore large mesocosms, but in this case, we use the small ones that you see lined up here. We have 9 of them. We set up a gradient of alkalinity enhancement, in this case with calcium carbonate. And on the right side, you see, and I'm not going through this in detail, you see all the various components of the ecosystem and their interactions that we are studying in these mesocosms. And you also see the ecosystem services that we actually look at. So we estimate carbon sequestration, we look at food production, and certainly at ecosystem health. So this is really to assess what environmental risks may be associated with ocean alkalinity enhancement. And we're just in the middle of the study, so I can't really give you too many results yet. And with that, I like to close with what I think is a very important message to send out when discussing any of these approaches, which is that none of the CDR approaches, should they ever be implemented, and I think a lot more research is needed before that can be considered, none of these approaches can replace avoiding CO2 emissions. Nothing is cheaper than avoiding CO2 emissions, and for none of the approaches, the risk will be minimal. So we will always take a risk. So there's no reason to take any of these approaches as an excuse not to reduce CO2 emissions. And I think that's a very important message that should always be included when we look at these approaches, even if some of them look very promising with a high potential. And with that, I thank you for your attention, and I look forward to your questions.
Thank you so much, Ulf. This was really exciting and a very nice overview of the different possibilities here. So I hope there are some questions. Maybe you can raise your hand or put an X in the chat. So Horst?
Yes, yeah, thank you very much. This was really enlightening for me because I never have heard about these things, I must confess. So it was really exciting. I was just wondering, I mean, it is a little bit, yeah, I think, what shall we say, frustrating maybe that a lot of research efforts have been done in certain directions and then they all of a sudden stop. For example, this whole thing about iron fertilization, where you say that there is a moratorium. Where is this moratorium coming from? So why can we say, okay, research has to stop here? And my second question in the same direction would be actually, now you have shown like 6 different methods how to do that, how to get rid of the CO2 via the head of the ocean. Is this the end of the line? I mean, in some way, it's probably more or less conventional methods. At least I got this idea from your talk. So maybe somebody could think a little bit unconventional, or would you say, there is nothing we should do in addition. There's no basic research we should do to find maybe some other ways to use the ocean, because using the ocean, of course, always could have a long-term, really devastating effect on the whole ecosystem or the whole system, and at some point in the future that we cannot foresee because it's simply too complex, the whole system. So is it too complex? We should stop it, or should we continue?
Let me first answer the first part of your question. There's 2 international agreements which have put a strong hold, I should say, not completely banned research, but put a strong hold on iron fertilization research. One is the London Convention and Protocol, which clearly states that dumping, including dumping of iron into the ocean, should not be allowed, with the exception of legitimate research. And the bar is put very high for what is considered legitimate research. And then there is the Convention for Biological Diversity, which in 2000 and I don't know when it was 12 or so, has also had an international moratorium on iron fertilization. They in fact put into their agreement that iron fertilization research should only be done in coastal waters, if at all, with again a high bar of being permitted. And in coastal waters, it doesn't make any sense because they're not poor in iron. So it's kind of, by formulating that, it's kind of bent altogether. There's certainly ways of still getting permission to do this, but the international science community is kind of scared to do it because it's considered a bad geoengineering approach. So let's not touch it. In terms of your second question, I think this pretty much the list I've shown. I mean, you can divide some of these approaches into various sub approaches, but I think it more or less covers the options that we have. That there may be still some surprises that we haven't really looked into so far. But in terms of what's scalable, what really has the CDR potential that is needed to make a difference, I think we've pretty much listed everything that's on the table.
Can you then just comment on this third method, which potentially has a high potential, and but is not investigated enough? And I think it was actually quite interesting because because CO2 is also needed for a lot of things that we might develop now, electrofuels and so on and so forth. And so it would be good to get it out of the water also at some point. And that seems to be the way you get it out and then press it in the ground.
Yes, I mean, you're absolutely right. It's in fact, it's considered by some of the chemical companies. We're talking with BASF on this issue, and they're actually considering the direct kind of concentration of CO2 from seawater as an option to get CO2 for further production lines. As a cheaper approach than taking it from the air, because as I mentioned, there's so much more inorganic carbon in seawater. If you acidify that seawater, the CO2 drives out, and you can concentrate it at much lower cost than you would take up CO2 directly from the atmosphere. So the approach in that sense has a high potential. The question is what you do with that CO2. I mean, the CO2 you take out, if it's taken out from the surface ocean, would be replenished by CO2 uptake from the atmosphere. So you would have the effect that is desired. But what then do you do with that CO2? If you use it for fuel production, that would be one option. If you sequester it into geological formations, that would be another option. Yes, the potential is high, but the disbenefits of where you go with it afterwards, I think, are also high. CCS is not really an option that is particularly high in public perception in Germany, at least.
Yes, but you would probably do less with the groundwater in the ocean. So you would disturb the systems probably less. But of course, you are absolutely right, and you never know what happens with the pressed CO2 around.
Yeah.
Yes, I'm living in an area here close to the border where there has been a very harsh discussion about this pressurizing CO2 in the ground, and there was not really a will to do that. That's true.
Yeah.
Thank you.
So, Ulf, I would also like to ask a question. And you had the coastal blue ecosystems on your list, and they were rated low. But as you also had in your table, there are also other co-benefits of, for instance, increasing biodiversity. And I'm actually doing some research on this, and we actually find quite high rates. And in a way, I'm working with seagrasses, and a lot of the seagrass beds, they have been lost over the years due to pressures in the ocean, eutrophication, coastal buildings and constructions and so forth. So I see a potential there that we can restore the seagrasses, and then actually by restoring them, we build up carbon pools in the ocean or in the sediments, and they also take up CO2 on a daily basis year round. I just wanted to maybe point out that maybe there's something more to be done there. The calculations we have done, if we restore all the seagrasses in Denmark, is that they can actually bury 2 years of CO2 emission in Denmark, or 2 years of Danish CO2 emissions. So it's low, but I mean, it is a contribution. So what do you think about that?
You're absolutely right. I think seagrass meadows, mangrove forests, and kelp forests, that's a no-brainer. I mean, anyone can agree on that. The co-benefits are huge of doing that. And as you also mentioned, it's not just the seagrass that sequesters the CO2, but the sediment that is kept together by the seagrass meadows that sequesters a lot of CO2. So absolutely, that's a good way forward, and it's easy to find public acceptance for that. But we also need to keep in mind the issue of additionality. I mean, are we just restoring a carbon pool that was there before, or are we adding a new carbon pool, which is the case also for a lot of forests? We have cut down forests. We can regrow them, but that's not kind of, it's just regaining a carbon pool that was there before. Is there anything, we need to get rid of all the CO2 that we took out of the ground by fossil fuel. That CO2 needs to be sequestered on top of just kind of regaining those carbon pools that were there before. So the additionality really isn't, I mean, is there a lot more space that we can use for seagrass meadows? And I'm not sure, you probably know much better. I think that's why it's considered low in potential at the moment.
Yes, yeah, I know the discussion. So, yes, but I think we could do something to restore it, at least to get the pools back, because we also need that. Yeah. So, but it's two different discussions. So I agree on that. Okay, I think we better continue, and then maybe we can have a few questions after the talk by Caroline. So thanks a lot, Ulf, for your presentation. And then I'll just say a few words about Caroline Løscher. Caroline Løscher is an associate professor at the University of Southern Denmark, or at the Department of Biology, where she belongs to the North Sea group, focusing a lot on ocean biochemistry. So you're also a biological oceanographer by training, and actually from Germany, but you came to SDU some years ago as a postdoc, and now you have a permanent position here at the university. You're also a fellow in the Danish Institute for Advanced Study, where we focus on interdisciplinary research. So you are really a broad scientist. So Caroline, with these words, I would like to give the word to you, and I'm looking forward to your talk.
Thanks, Marianne. That is really sweet of you. I'm just trying to figure out what I do, and
yeah.
I think this one should be it. Is it the right thing?
Yes, it's and perfect in the presentation mode as well. So
fantastic.
Just go ahead.
It usually never works the first time I try. So I also want to quickly thank Ulf for his presentation. I think that was really a nice overview. Now, there is, of course, a certain degree of repetition here that comes from the fact that Ulf and I are working on closely related topics. It also comes from the fact that Ulf actually is one of my former academic teachers and was a good and long colleague for many years, actually, after I was a student. So my work is always somewhat inspired by what he is doing. Though repetition is not a bad thing, I guess, and it always helps us to learn the subject a bit more. So I will talk a bit about the Danish twist of the story, where I try to basically contribute to what Denmark has set as a goal, a pretty ambitious goal to become climate neutral within the next 10 to 20 years, which seems very ambitious, and hopefully it has some sort of touch with reality. My approach to it is as also Ulf's is ocean alkalinity enhancement, and this we try in my project to apply to Danish waters, and essentially then also upscale it, as Ulf put forward. Scalability is an important point, to make it actually useful to contribute to a removal of CO2 around Denmark or connected to Denmark, which is also, of course, useful for other areas. I repeat a bit on the carbon pump. Ulf already put forward that the ocean has a huge potential to remove CO2. It's a quarter of what we have as a standing stock, and it does so continuously via two pathways. One of them is the biological carbon pump, of which Ulf and I are big fans, as it has to do with life, and it essentially describes how phytoplankton and little plants, or even bigger plants, remove CO2 from the atmosphere using the power of sunlight. And this process is, of course, an important one, and was also subject of the iron fertilization experiments. But one needs to also do some sort of reality check here, as the permanent export of it is nice, as it's a long-term one. However, it is not as big. It's only a minor percentage of the whole carbon fixation that goes into export and fossilization and permanent removal of CO2 from the atmosphere. Most of the CO2 is recycled, though. So it is. There's another way, however, to take CO2 out of the atmosphere. This is the chemical dissolution, and that is actually quantitatively quite huge. So there's permanently some dissolution of CO2 into seawater, as Ulf already put forward. It dissolves into carbonate, bicarbonate ions, and is more or less then present as a standing stock. This is a good thing. And it's a natural thing to happen. However, if CO2 in the atmosphere increases, the problem is that the waters acidify during this process, as we have just a split off of certain ions, and this just decreases the pH. So this is a problem, and it is also a massive problem in Danish waters. We have this, we find ocean acidification all around our coastal waters, never mind in the Baltic or in the North Sea, and especially also in our fjords, like Mariager Fjord and Limfjorden, which are extremely acidified over many years until now. A second problem that goes hand in hand with the ocean acidification is a loss in biodiversity. And this is actually on all levels, and this is also what I assume why Ulf's group and Ulf's team for the mesocosm study is paying special focus on this. It is it basically spans from bacteria to phytoplankton to even up to fish, which may reproduce on a lower level than if waters acidify. What's especially interesting to biogeochemists like me, Marianne, and Ulf is that the primary producers who actually do fix the carbon via photosynthesis often have shells and cannot form their shells or maintain their shells if waters acidify too much. So this is actually a general problem. And if we lose those organisms, that is, of course, a problem as it spans through the food web, and we lose all kinds of organisms. In the end, it will affect us humans as the fish stocks decrease. So this is generally not a good situation. Sorry, I have a bit of a cold. It's not Corona. So what we actually would like to do is to do something about both ocean acidification that we have present in Danish waters all around the coast, and maintain the biodiversity while we remove CO2 from the atmosphere. And just to show you how different our waters around Denmark are, we see that they have, we have the North Sea water. This is extremely saline water from the Atlantic. We have then a zone where water masses mix, and then we have the classic Baltic Sea water with low salinity. Salinity is an important factor of how much CO2 can go into the water. So we have very different challenges all around Denmark's coast to fight ocean acidification, but also different potentials on how to remove CO2 from the atmosphere. The trend is that acidification will increase massively no matter where we are around Denmark. This is here shown by the red line, right? The pH goes down, so waters acidify. This is, of course, bad news for us in Denmark and Germany, everywhere around the Baltic and the North Sea. But it also is a potential, right? Because this is something we can actually directly approach with this, highly potent approach of ocean alkalinity enhancement, meaning essentially to add those alkaline minerals into the water column, which way ever, to mitigate this ocean acidification while we protect the little organisms with the shells or without shells, and while we actually try to shift the balance towards carbonate and bicarbonate ions, so to remove more CO2 from the atmosphere. We can do that, as Ulf already put forward, in different ways. We can throw minerals on the coastline, essentially, to let them naturally transport in. Their approaches like this under construction, more or less, in the Netherlands, and there are a bit more elaborate approaches about this already available from Portugal. So it seems, as the Portuguese colleagues could find out, that it is connected to a lot of loss of minerals if we just pour it on the coastlines and hope that it's naturally transported into the water. We can also, supply the water the one or the other way directly by either pouring it from a ship or from a helicopter into the water, so that we target certain areas specifically and try to basically fight ocean acidification and enhance CO2 uptake from the atmosphere at the same time. So what we were trying to find out was now how to do this in Denmark. The research status when I started this project was essentially, kind of not existent. There were beautiful calculations and data sets available from a colleague of ours, Phil Ranford, from Scotland. And Phil did some different calculations on how much CO2 can be bound or can be removed from the atmosphere by the addition of different minerals. And he figured out that, for example, olivine and lime, but also dolomite, calcite, and other minerals could be useful. Phil did this on a theoretical background, the background that Ulf also introduced to you. So how many ions can be bound if you add some alkaline minerals? So it's a more or less theoretical consideration, which you need for getting started, and which gave us all the momentum to actually get started, because we thought this is something to really look into. However, there were many open questions. We didn't know about the dissolution kinetics, meaning like how do we dissolve it at all? How do we dissolve essentially stones in water? Then we had no idea, of course, what will happen if we do so, right? We do understand marine chemistry, how the seawater functions, how it works to take up CO2, but we had no idea if we shift anything for the better or the worse, if we just randomly add minerals. It was even worse for biology. No one can still, I think, really say what will happen to biology, and we will have to really carefully test how we impact biological systems when we pour in minerals into the water column. You can imagine if we just grind them down to dust, throw them into the water column, that makes the water column kind of dark, because there's a lot of dust that doesn't benefit photosynthesis and could actually also clog some organisms' pores. Could also be that fish are not especially happy about this, so this also needs careful evaluation. And we also until now do not have a real understanding of potential dangerous side effects, like, for example, again, similar to the iron experiments, the production of other greenhouse gases like methane or CO2, which can result from experiments like this. Yes. So this was basically where we started from, and this was how my group started from it. So we essentially ordered minerals of interest to us, and they arrived in our lab in this shape. So we had to first challenge on how to dissolve them in Danish waters. So we took our artificial seawater, our Baltic seawater, our water from the Danish fjords and the North Sea water, and tried it, right? You have to try it. First trial was, of course, how to get it into powder. And as Ulf already said, you have to really grind it down to very small particle sizes. A maximum of this is around 60 micrometer, and an ideal would be around 10. So this is not only difficult, technically just difficult, but it's also energetically costly. So we actually invest CO2 in order to bind CO2 in the end, and have to be really careful to find the right threshold here, the right trade-off. We found some trade-off and could grind them down to the desired sizes without using all too much energy on it. Actually, also this shows that we need to create alternative energies more and facilitate them more to make them actually also usable for approaches like this. Then, however, it was not done because we had to get it dissolved in seawater, and just having it in a small particle size didn't totally help this, because we got to a really sobering result here, which you can see here in the blue part of the panel, where you can see how much percentage-wise dissolved actually in the water, and this didn't look so good. It was actually only between 1/3 and 60% at the absolute maximum that dissolved in the seawater, and the rest would just sink out. So that of course is problematic if we have this, right? Because then the whole calculation as we had it, that so and so many tons of CO2 can be bound by the mineral, actually has to be downwards corrected quite significantly to 1/3 or half of it. And that is of course makes it a bit less attractive. So we, of course, couldn't accept this and tried around and tried to figure out what seawater concentrations of minerals work well. We did a whole lot of experiments, and we found some of them that worked okay in a satisfactory way, maybe, and are still have a lot of room to improve. What I'm showing you here is essentially just the pH value that we tried to increase a bit to avoid acidification, because this is a graph that is quite easy to understand. And we let an experiment run over like a bit more than 3 months to see how long the effect is, how much we need to really add to bigger seawater bodies to generate a proper effect on the ecosystem and on the water column per se. So we figured out that actually 2 minerals work better than the others. Those are olivine and dolomite. Both actually can achieve the perfect effect of stabilizing the pH in a bit of a higher range, so fighting ocean acidification. At least in North Sea water, that worked quite well. In other waters, it unfortunately looked a bit differently. So this would also mean that we need to carefully evaluate if this is an approach that works then everywhere, but so it is. Some of our minerals caused an opposite effect, which was is still not totally understandable to us. We understand it as some sort of precipitation from seawaters that actually then lower the pH. That would be a problem if we applied this on larger scales. So we followed up the ones that actually were functional, which are olivine and dolomite. We then wanted to make sure that we do not kill organisms with our idea of fertilizing, for example, Limfjorden with our alkaline minerals, and we used a couple of different algae. I'm always showing a picture of how those algae look, because I think most people have no good impression of how our work really looks. And also algae are just really beautiful, as they don't only come in green, they can take all kinds of colors. And this is always very impressive to me. I'm showing you an example of one algae that is actually pretty much abundant everywhere in the ocean. We find it throughout. It's an organism called Micromonas, a little green algae, and it is pretty important for carbon fixation. We also have it in Danish waters, in Limfjorden especially, and in the North Sea impacted water masses. So Micromonas we exposed to, this is how it looks, we exposed to different minerals. We used olivine, dolomite, and also lime, because this is often suggested to be used, and just try to understand how it fixes carbon and how it grows, essentially. So as a measure of whether we damage those organisms or not. It seemed that those organisms did actually grow under every condition pretty much the same way. So there was no real really impressive difference, which is actually good. So we didn't have any negative effects, meaning we didn't kill anyone. That is good. We also didn't have any big facilitation of growth, and this is actually also not bad. That may now be a bit counterintuitive, because one would think if we have more algae growing, they can fix more CO2. But especially in Danish waters, this would actually be a bit of a problem. Because if we in Denmark now fertilize the ocean in a way that we have more algae growing, we do actually maybe short term remove a bit CO2, but we already have a significant problem of algae blooms in our coastal waters, and not only in summer, but mostly. And this is due to our heavy land use, to agriculture essentially, and the fertilizer runoff from the countryside into the water. And this is a permanent problem in Danish waters. And if we would now cause a similar effect, this would not be a useful strategy for our own coastal waters here. This massive blooming of algae in coastal waters means oftentimes that the algae also die at a point, of course, sink out to the seafloor, and the seafloor in Denmark is not very far away from the surface. It's only a couple of meters. And then they degrade, leading to oxygen consumption. And this actually leads to massive losses of oxygen all around the world if stuff like this happens, but especially in our Danish waters in the Baltic Sea, but also in the coastal systems of the North Sea. So we cannot risk this, and it's actually therefore good news if we do not now facilitate blooms of one of our major algae in our system. Still, this needs a bit more testing. We tested until now like 40 organisms, and we're still doing more because we lack the basic understanding of what those alkaline minerals are doing. I also hope that we can learn from Ulf's larger scale experiment how whole communities will respond to mineral additions like those. And I hope there's a certain possibility to transfer it from one ecosystem to the next one. Another problem that I'm now taking from a really old paper of mine is the nitrous oxide problem. As I said, we might run into the danger that while removing CO2 with this approach, we could probably promote the production of other greenhouse gases. Nitrous oxide is an especially dangerous one, as it's 300 times as strong as CO2. In this old study of mine, I just measured nitrous oxide production over different pH variations. And I found at that point some years ago that essentially, whenever you're out of the normal range of what seawater usually has, you're amplifying nitrous oxide production massively. If we now assume that we increase the pH to a certain level by adding those minerals, we could possibly, just by doing this and by a couple of other effects too, facilitate nitrous oxide production. And this is, of course, again, a total knockout criteria, which we need to make sure that it doesn't happen in our waters as we apply ocean alkalinity enhancement. So enough for the bad side, but it has to be really clear what we are doing here before we apply it. Well, now comes the applicability problem. As Ulf already put out, it is actually, it has different sides. One of the sides is a diplomatic problem. We are not allowed to just throw stuff into the ocean. We cannot. The bar is really high, and it's not easy to justify. We can do in local waters if we get a permission for this. This requires, for me, for example, a pretty close collaboration with the Miljøstyrelsen, the Environmental Ministry of Denmark, who are right now really helpful, but other places are less so. So it's not always easy. In any case, right now, my group and we are doing some experiments off the coast of Mandø and Færø, which are here, the southernmost areas. I highlighted with an arrow here. So connected to the North Sea, we do experiments in Limfjorden, as there is a good long-term data set on the alkalinity and so on available from the Aarhus University. And we also work in the south of Fyn right now to compare it to a Baltic Sea situation. A previous study was in the area around Mariagerfjord, and yeah, we will also follow this up again at a point. So we were thinking about how can we apply this, as we had permission to do so for a bit. So we got inspired by a couple of colleagues from Sweden. They were doing this. They took helicopters and used basically the pouring out over lakes just as their major approach. That worked pretty well for they have pretty acidified lakes and riverine waters in Sweden, and they did this mainly to basically buffer the acidity, to basically increase the pH. That worked well. As in Sweden, there is obviously around the lakes not a lot of wind, and so there's not much loss of the minerals. I imagine if we tried a similar approach off the coast of Germany or Denmark, we would get everything into our eyes in the next best town, and it would just fly away, decreasing our efficiency again. Another thing that was, however, pretty impressive to us was this. It looks maybe not very impressive, maybe rather like a public toilet or so, but it is actually a nice idea, and we actually reconstructed a smaller prototype of this now, and it is actually a silo in a sense, right? So there is a big mineral container on top of this whole situation, then followed by a pump and vibration system, which pumps water through a place where the minerals then slowly dissolve and actually heavily shakes the whole water body with the minerals in it, pumps and circulates this in a certain way a couple of times, and then basically lets it out into the rivers in the case of Sweden. But also one can use this for mounting it actually on the windmills that we have in the Danish waters of the North Sea. So we could build something similar, which we now did in form of a prototype, and basically install it along our coastlines and in our fjords. I found this kind of impressive because the researchers in Sweden were really thinking ahead. They are driving this whole machinery with a solar panel, so they are actually CO2 neutral with it, if you ignore the costs of CO2 of construction here. So this seemed to me to be a convincing approach to make applicable for ocean settings. And so we did right now, and we will try and install some of them at those 3 spots that I point out here in the map. So in Sweden, they were actually quite successful with this, and they can add between 30,000 and 200,000 tons of CO2 per year into their waters. That is really a lot. If we think again a bit about what that means, right? We might be able to bind maybe a third or half of the number of minerals added to a system. We may be able to remove this in terms of CO2, ton CO2. So that could be an attractive number, if true. It is probably a bit optimistic, but if we would install those machineries in the same frequency and the same number as in Sweden, we could probably make it useful for contributing to a more positive budget of CO2 in Denmark. We have to work, of course, on improving the dissolution efficiency, because the minerals do not dissolve well. And even if we use the approach that Sweden uses, is not it's not perfect, and this will be the place where we have to actually invest some more work to optimize this, because yeah, that is an important part of it. Then we will have to test our prototypes, of course, in the waters in situ, and not only in our labs in a container. That will be, of course, a very important step, but only to put it a bit into context, right? If we think about those numbers, it's actually quite a high number. If we think about that, it was pretty hyped in the press just some weeks ago that Iceland now has a first carbon capture plant. It removes 4,000 tons CO2 per year. This is actually way more that Sweden can remove with their approach of a natural based solution, which I find also always the preferable way to do it. So yeah, we were a bit more technical and tried to make it really applicable for the waters of Denmark, and we are still not far enough, but on a good way, I think. We're trying to team up now with industrial partners, and I hope that next year I can give you a pretty positive update on how our prototype worked in Limfjorden and off the coasts of Denmark. For now, I'm done, and I want to thank you for your attention. I want to thank my funding agencies, especially the Willum Foundation, but also the DIAS, the EU, and the DFF for always supporting me in my research. I also want to thank my team. I think a lot of the work has really been done by my PhD student Jakob, together with my technician Sarah, who are very enthusiastic in this project. And yes, so thanks.
Caroline. Yeah, it was a great talk as well. Are there any questions for Caroline? For the more, you can say, more practical studies here? Horst, I think you opened up.
Yes, I did not, but I have a question actually, because now, first of all, thank you very much for this talk. And again, I feel a little bit more familiar with this topic now. That's good. But you confused me a little bit, because I understood actually that Limfjorden is a bad idea to make these tests, because you have this algae blooming thing.
Yeah.
But now you do it anyway there.
Yeah, Limfjorden is not one water body, right? It has a couple of different parts of it. What's nice about Limfjorden is that it's, or what's not nice is that it's pretty acidified. It's a problematic environment, so it deserves special attention, right? What is of course bad is that it's eutrophied, highly eutrophied, right? As it's in the middle of a bigger landmass of Denmark, and you know that fertilizers, of course, are just like massively supplied to our countrysides and come into Limfjorden, and so lead to the eutrophication there. What we use is this area around the time series station of the Aarhus University, where we actually are quite in control of when the algae blooms are, and we can actually then choose wisely pretty much on when to try it out. And I think it's also it's not the most optimal place to do it, you're right, but it is for the sake of proving the concept and seeing if it works and if the effect is a proper one and is worthwhile pursuing, it's a good place, as we have a good understanding of the system.
Yeah. And then I thought your little remark about what is happening at Iceland and the amounts that are removed of CO2, if one puts that in context with the gigatons that we need, this is a little bit ridiculous, right? If this, it's not a short-term solution, at least. That's for sure.
There was a comparison that it equals the production of CO2 in 1 second. So, like, yeah.
Yes.
So that is depressing, of course, right?
Yeah, I take Ulf's note that we should better avoid CO2 emissions as a very serious note, actually.
Absolutely, that's always right. That's never wrong. Ulf.
Yeah, thanks for a very nice presentation. I was surprised to see that you actually got permission to do alkalization in Danish waters. In Germany, this is completely a no-go. I mean, in our project that has just started, we were not allowed to do any field testing at this point. So before knowing what negative side effects there may be, how does the permitting agency in Denmark kind of grant these permissions? On what basis do they do that?
So yeah, so here it's the environmental ministry, the Miljøstyrelsen, as we call it in Denmark, that does that, right? And one good thing about Denmark is that you know, you can call them. It's a small country, and talk to them, right? It's quite easy. They're also located here in the same city as we are, so the communication is very easy. So they said, I need to make sure that there is no, you know, poisoning. No, nothing happening like this. So what we did in the first place was doing a month of monitoring of a water body that we actually carried to our lab, added the minerals, and then, you know, tried to ventilate it enough so that stuff is not impacted so negatively, and then basically showed that there is no like massively dangerous effect. We fed a bit of nutrients, which was maybe a bit unfair, but you know how it is, if you just let it stand, it will die. So we had to show that not everything dies. We had to show that we had to actually also show some lethal rates of we used copypodes. So we had to basically add as much as it kills them, and you need a lot to kill them. So that was okay, and then had to promise that the dose is not even close to this, but decrease it by 3 orders of magnitude. That was okay. And then essentially in the next step, we had to promise that we do it in a closed tank and not release the water to the environment. And as this was okay, then now they are kind of more open, but it's still to deploy, for example, the pumping system, the silo, right? We are a bit far away from this still, right? So it's they are considering it, but they might consider it for a pretty long time, right? So we do not know. But I would say generally, if you compare Denmark to Germany here, it's a bit more straightforward, as the country is small and you can really just talk to people, and it's not so bureaucratic in a way. I mean, that's pretty much all you can say to it. That's the advantage. Yeah.
Excellent, Caroline. We are running close to the time, so maybe one short question. Ulf, I don't know if you had finished. Okay, then just maybe short, Caroline, upscaling. You mentioned this with the windmills, that you could foresee that it's something we could place on the windmills out in Nordsee. I was
Yeah.
Yeah.
That was kind of an idea that I discussed with also one of the bigger funding agencies here in Denmark, because that will require a bit of additional funding, of course, and a bit more of technology development funding. And that suggestion actually came from them.
Okay.
So yeah, it's in the future, but I don't think it's all too far in the future to at least get a positive response from a funding agency here so that we can start building. That would be nice, of course, but upscaling is always a problem, right, for us, and it's a problem from a diplomatic perspective. It's a problem from a technical perspective, but we got to start somewhere, I guess.
Yes,
So,
you're right.
Yeah.
Okay, thank you. Then I'll give the word to Horst.
Yes, thank you very much. But I had also a little remark, because I think this upscaling, then you should think about involving the Faculty of Engineering. So when I saw this little tank, I think from Sweden, we could do a little bit better there. Okay.
Look, I guess there is a lot of room to improve that, and,
Yes.
and I'm happy to collaborate with the technical faculty really a lot. That would be very nice, I think. So,
okay,
so, yeah.
Thanks. Let's take that for the future. So thank you, everybody, very much again. Thank you very much, Marianne, for leading or chairing this session. I think it was a highlight for the conference, at least for me. I learned a lot of new things, and I hope we will continue this topic in the one or other way also next year on the conference, when we're continuing physically here in Sonderborg. And with that, I think I would also like to close that here, because we should all go back to the main room now, where we will continue the conference. Thanks a lot. Bye-bye.